Good day everyone. Today we have an activity about blood stain pattern analysis and blood spatter analysis. But before we begin, I would like to introduce the materials that we will be using or needing for this activity. We have here our cloth, tumbler with hot water inside, coloring powder, Nescafe. Also, we have our push pins here, ketchup, cornstarch, push pins, basin, cardboard sheet, and yardstick. Magnifying glass, yarn, syringe, evidence tents, cordon, sponge, spray bottle, scissor, brush, wipes, ruler and protractor, glass, bond paper, evidence bag, dropper, compass with pencil. That's all of the materials we need for this activity. Preparation of fake blood. Now let me show you how we prepared our fake blood. First, pour a moderate amount of hot water into an empty beaker. Then now, add the cornstarch and stir constantly until it blends well and becomes thick. Stir continuously until it dissolves and mixes well. Keep stirring until you achieve the right viscosity. Next, add the coffee powder to increase the thickness and darken the color. Then mix it again. Finally, we tested it on non-porous surface to check if the viscosity is ready and good to use. Single drop. In this activity, we created a single drop by releasing blood from a fixed height onto a flat surface. The stain formed a circular shape due to surface tension. After performing this, we measured the stain and estimated the width and length to be approximately 1.5 cm by 1.5 cm. This indicates a 90-degree angle of impact. In a real scenario, this may represent a person standing still while bleeding, where blood falls straight down. Drop series. After doing this, we measured one stain and estimated the width and length to be around 1.4 cm and 1.6 cm. This pattern indicates movement that can help determine the direction and speed of a wounded individual walking away from a scene. In this slide, we are looking at what we called a passive blood pattern. You can see a trail of blood stains forming a line, which is known as a blood series. We measure the width and length of this void, which matches the shape and size of a shoe print. We also measure the stains and distance along the trail. Drop series with void area. But notice the gap right here in the middle. That space where there are no stains is called the void area. This happens because something was present at the time the blood was being deposited, like an object, which blocked the blood from hitting that specific spot. When that object or person was removed, it left behind this empty. Flow pattern. A flow pattern is a way of blood spreads or moves on a surface after impact. After performing this, we measure the stain and estimated the width and length to be approximately 1.8 cm by 3.0 cm. This pattern can indicate the angle of the surface and the direction of the blood flow, such as blood running down at a wall. We poured a larger amount of blood in one spot to form a pool. The blood spread outward, forming a large irregular stain. After doing this, we measured the spread and estimated the width and length to be around 4.5 cm by 5 cm. This suggests prolonged bleeding in one area, such as victim in remaining motionless. Now, compare this to the same amount of blood dropped onto an absorbent cloth. Instead of staying in a neat pool like it did on glass, the blood soaked right into the fabric. It spread out more, looking larger and darker with fuzzy edges, because the material absorbed the liquid instead of letting it sit on the top. Impact spatter. We created an impact spatter by striking blood-soaked sponge. The droplets spread outward from the point of impact. After performing this, we measured the droplets and estimated the width and length to be around 2 cm width and 3 cm length, 3.2 cm width and 4.3 cm length, 4.7 width and 5.0 length. The pattern suggests blunt force trauma such as hitting with an object. Cast-off pattern. We created this by swinging a blood-covered brush. The blood formed linear patterns due to centrifugal force. After doing this, we measured one stain and estimated the width and length to be about 0.3 cm and 0.8 cm. This pattern indicates repeated motion such as multiple swings of a weapon. Arterial spurting. We simulated arterial spurting using a syringe producing a pulsating pattern. After performing this, we measured the stains and estimated the width and length to be around 0.5 cm and 1.5 cm. This pattern indicates blood being pumped from a damaged artery. Contact pattern. We press a blood-covered hand onto paper, creating a clear imprint. After performing this, we measured the stain and estimated the width and length to be around 8 cm by 10 cm. This pattern can help identify objects or individuals present at the scene. Swipe pattern. We drag a bloody object across a clean surface. The stain started heavy and gradually became lighter. After doing this, we measured the pattern and estimated the width and length to be around 5 inches by 5 inches. This indicates the direction of movement. Wipe pattern. We drag a clean object through an existing stain, altering its appearance. After performing this, we measured the disturbed area and estimated the width and length to be about 3.3 cm by 6.3 cm. This indicates interference after the blood was already deposited. We dropped blood from a fixed height 3 feet and observed its structure. We identified the parent stain, spines, and satellite spatter. After doing this, we measured the main stain and estimated the width and the length, that is around 2 cm by 2 cm, with smaller surrounding droplets. The overall shape and features of the blood drops track the surface at a 90-degree angle, falling straight down with enough force to create these distinct characteristics. Part 3. Effects of surface textures on blood spatter. As you can see here, surface texture is a very important factor in forensic analysis. Blood doesn't look the same everywhere. It changes depending on what it lands on because of differences in surface tension and how much the material can absorb liquid. In this experiment, we tested 3 different types of surfaces: smooth surfaces like glass, rough surfaces like concrete, and absorbent surfaces like fabric. We dropped the blood from the same height of 4 feet to make sure the results were fair. On a smooth surface such as glass, the blood form slightly resembled a small pool central stain with maximal disruption. We measured the main stain and estimated the width and length to be around 9.0 cm by 10.3 cm. On a slightly rough surface like concrete, the stain showed visible spines and more satellite droplets. The main stain was measured approximately 2.8 cm by 6.0 cm. On an observant surface such as fabric, the stain appeared irregular and partially absorbed with many surrounding droplets. The main central stain measured approximately 3.2 cm by 5.3 cm. Part 4. The effect of falling distance on blood stain morphology. 1 foot. For the first drop, the stain appeared circular with smooth edges measuring 1.5 cm by 1.5 cm. For the second drop, the result was identical, also measuring 1.5 cm by 1.5 cm. For the third drop, the stain remained consistent with the same measurement of 1.5 cm by 1.5 cm. At this height, we observed no satellite spotters and all stains were uniform in size and shape. This indicates that at a lower height, the blood drop has less impact force, resulting in minimal spread and no fragmentation. 2 feet. At the first drop, the stain appeared slightly larger than at 1 foot, measured approximately 1.5 cm by 1.6 cm. For the second drop, the stain measured around 1.6 cm by 1.6 cm. For the third drop, the result was about 1.6 cm by 1.7 cm. At this height, the stains remained circular with smooth edges and no satellite patterns were observed. This indicates that while the height increased, the impact force was still not enough to cause fragmentation of the blood of drop. 3 feet. For the first drop, the stain measured approximately 1.7 cm by 1.7 cm. And the second drop, it measured around 1.7 cm by 1.8 cm. For the third drop, the stain measured about 1.8 cm by 1.8 cm. At this height, the stain showed slightly larger diameters but still maintained a mostly circular shape. Similar to 2 feet, no satellite patterns were observed, suggesting that the drop had not yet reached a velocity high enough to break apart upon the impact. 4 feet. For the first drop, the stain measured approximately 1.8 cm by 1.8 cm, with visible satellite droplets surrounding the main stain. For the second drop, the stain measured around 1.9 cm by 1.9 cm, also showing satellite droplets, and in this trial, light spatter would observe, indicating partial breakup upon impact. For the third drop, the stain measured about 1.9 cm by 2.0 cm, with satellite droplets present but no significant spatter beyond the immediate area. Part 5. The geometry of angles of impact. In this part of the activity, we examine the angle of impact affects the shape of a blood stain. The objective was to understand how the length and width of a stain can be used to determine the angle and direction of travel of a blood droplet. We place a sheet of paper on an adjustable platform and set the angles at 90 degrees, 60 degrees, 45 degrees, and 30 degrees using our protractor. From a constant height of 3 feet, we release a single drop of blood for each angle while keeping the dropper vertical. Each stain was leveled and measured in terms with width and length. The direction of travel was identified by the pointed or narrow end of the stain. When a drop falls at 90 degrees, it forms a perfect sync circle because the width and length is equal, resulting in a ratio of 1 and confirming a vertical fall with no horizontal movement. As the angle decreases to 60 degrees, the stain becomes slightly oval, showing a small difference between width and length, which indicates slight horizontal motion. At 45 degrees, the blood stain becomes more elongated, forming a clear elliptical shape with a noticeable tail that points in the direction of travel, showing the drop move diagonally before impact. At a lower angle like 30 degrees, the stain is highly stretched, with a much smaller width compared to its length and a more pronounced tail, indicating that the blood was traveling almost parallel to the surface. Overall, as the angle decreases from 90 to 30 degrees, the shape of the stain transitions from circular to increasingly elongated, and the tail becomes more visible, helping identify the direction. Part 6. Tracing the source 2D to 3D correct construction. In this activity, our goal is to determine the area of convergence and the area of origin of a simulated bloodletting event using stringing and trigonometry. Procedure: creating the blood stains. The first thing we did in this activity was to create a splash of blood on a flat surface using tarpaulin. After that, we carefully observe and measure all 20 blood stains, focusing on their width and length from where the drop started until it formed an elongated shape. Step 1. Area of convergence and angle of impact. We determine the area of convergence by observing the direction of each blood stain instead of drawing lines. The narrow end of each stain shows its direction of travel. By tracing this direction backward, we identified the point on the surface where the blood likely originated. After that, we calculated the angle of impact for each stain. We measure the width and length of each blood drop and use the formula R seen width divided length. This helps us determine how the blood droplets struck the surface. Step 2. Area of origin. To find the area of origin, we use the stringing method. We attached strings to the blood stains and lifted them using the calculated angles of impact. Then we extended the strings toward an area of convergence and point where the strings meet or clustered, and a space represents the area or region of origin, which indicates the position of the blood source during the incident. In conclusion, the region of origin, axis of origin, and area of convergence are all important in reconstructing a bloodletting event. The area of convergence helps identify the exact point on the surface where the blood stains meet, showing the possible location of the incident on a 2D plane, and the axis of origin is important because it shows the vertical directions of the blood source, helping investigators understand the height and position of the impact. Lastly,
The region of origin is important because it gives a 3D space or zone where the blood source likely came from, allowing a more accurate reconstructions of what happened during the event.